So welcome. My name is Dan McKinsey. I'm a professor at the UC Berkeley Department of Physics and the vice chair for faculty. Tonight is my great pleasure to welcome you to the annual Emilio Segrè Lecture. Berkeley physics has a distinguished history marked by both world-class research and dedication to a public mission, making higher education more accessible to California's citizens. We're proud to be a part of the world's finest public university. Our department's rich history includes Ernest Lawrence's invention of the cyclotron, giving birth to the field of high-energy physics. It includes Robert Oppenheimer, who attracted to Berkeley a generation of brilliant theorists, and it includes the person we honor tonight, experimentalist Emilio Segrè. Each fall, we celebrate Segrè by bringing to Berkeley renowned experimentalists. Since 1987, these scientists, through their research, have changed the way we perceive our world. Past Segrè lecturers include Nobel laureates Bert Richter, Masatoshi Koshiba, Stephen Chu, Hans Bethe, Art McDonald, Dave Wineland, Ray Weiss, and Taka Kajita. Past lecturers also include Millie Dresselhaus, Robert Sokolov, Xiaowei Zhuang, and department member and former chancellor Robert J. Bergeneau. Segrè received his doctorate in July 1928 from the University of Rome, working with Enrico Fermi. After 2 years in the military, he returned to Rome, becoming an assistant professor in 1932. In 1935, Segrè became professor and director of the physics laboratory of the University of Palermo. Soon after he made his first visit to Berkeley, Lawrence gave Segrè a strip of molybdenum that had been irradiated in his cyclotron. In Palermo, Segrè and his colleague Carlo Perrier extracted from that strip a previously unknown and unstable element, technetium. This was the first discovery of an artificial element, an element absent in nature. 15 years later, technetium was detected in stellar atmospheres, proving that certain stars continuously synthesize heavy elements. In the summer of 1938, Segrè returned to Berkeley to continue his work. While he was in the US, Mussolini's government passed laws that barred Segrè and other Jews from universities. Lawrence offered Segrè a position as research associate. Segrè accepted and brought his wife and young son from Italy to join him. With the war depleting Berkeley faculty ranks, Segrè became a lecturer in the Berkeley Physics Department in 1941. In 1943, he accepted Oppenheimer's invitation to join the Manhattan Project at Los Alamos, where he headed a group measuring fission rates. He returned to Berkeley after the war ended. In 1955, Lawrence and colleagues designed the Bevatron to produce 6 GeV protons, an energy sufficient to produce proton-antiproton pairs in proton collisions with a stationary target. Later that year, the discovery of the antiproton was announced in a paper by Chamberlain, Segrè, Wineland, and Ypsilantis. Chamberlain and Segrè were awarded the Nobel Prize for this discovery in 1959. Segrè continued teaching and research at Berkeley to and beyond his retirement in 1972. Over his 5-decade association with Berkeley, Segrè trained 30 PhD students, including C.S. Wu, Herb York, Tom Ypsilantis, and Herb Steiner. 1989, at the age of 84, Emilio Segrè died from a heart attack while walking near his home in Lafayette. Segrè was an avid photographer. After his death, much of his physics collection was donated to the American Institute of Physics, preserving a record of physics before, during, and after the war years. Now it's my great pleasure to introduce my colleague, UC Berkeley Physics Associate Professor Gabriel Orabigan, to introduce tonight's Oppenheimer. Segrè Lecturer, Dr. Fabiola Gianotti.
Good evening. I'm Gabrielle Arabi-Gann. I'm in the physics department here on campus, a professor of nuclear and particle physics, and it is my very great pleasure to introduce tonight's speaker, Dr. Fabiola Gianotti. Dr. Gianotti is the Director General of CERN, the European Laboratory for Particle Physics. She received her PhD in experimental particle physics from the University of Milan, Italy. Since 1994, she has been a research physicist at CERN. She worked on several CERN experiments covering detector R&D, construction, software development, and data analysis, the full end-to-end chain of these large experiments. From March 2009 to February 2013, she was the spokesperson, the head of the ATLAS experiment at the Large Hadron Collider. It was during this period that ATLAS and the CMS experiments announced the discovery of the Higgs boson. She has served on several international committees in Europe and the United States and received 15 honorary doctoral degrees from universities across the world. She's a member of 8 academies of science worldwide. She was awarded the honor of Cavaliere di Gran Croce dell'Ordine al Merito della Repubblica Italiana. And my apologies to the Italians for mangling that. She shared the 2013 Special Breakthrough Prize in Fundamental Physics and the Enrico Fermi Prize for the Italian Physical Society, and in 2019 received the Tate Medal of the American Institute of Physics for International Leadership. She was ranked 5th Personality of the Year in 2012 by Time magazine. I imagine that's rare for a physicist. Appointed Director General of CERN in November 2014 for the period from 1st of January 2016 to the end of December 2020. In November 2019, she was appointed for a full 2nd term. This is the first time in CERN's history that a Director General has been appointed for a full 2nd term, and she is the first woman in this role. Many firsts. I had the great privilege of meeting Dr. Gianotti for the first time this morning, and I was struck immediately by the warmth and the humanity that she brings to the role, which, coupled with the scientific brilliance and creativity, have really allowed her to shape not only the role of Director General, but really the direction of the laboratory itself. She stands as a remarkable example of scientific excellence and leadership, and of how curiosity, rigor, and compassion together can transform our understanding of the universe. An inspiration to so many of us, tonight Dr. Gianotti will present the Higgs boson and our life. This presentation will highlight how CERN's groundbreaking discoveries, like the Higgs boson, continue to shape science, technology, and our understanding of the universe. So please join me in welcoming Dr. Fabiola Gianotti.
Thank you. Good evening. I'm extremely honored and pleased to be here tonight and to give this distinguished lecture. I've chosen the title, The Higgs boson and Our Life, because I would like to illustrate the impact of fundamental research on our everyday life, not only because of the knowledge that it produces and generates, but also because of the technologies that we develop and the values that fundamental research promotes. And allow me to start with a couple of personal remarks. I'm very happy to be here for 2 main reasons. The first one is that over the past years, actually decades, had the privilege to work with many dear colleagues and friends from Berkeley, excellent scientists, excellent physicists, engineers, and technicians in the framework of the ATLAS experiment at the Large Hadron Collider. And the second reason is that Emilio Segrè is a legend in Italy for particle physicists like me, a nuclear physicist. He was a member of the group called I ragazzi di Via Panisperna, the Via Panisperna's boys, a group of phenomenal physicists who work at CERN at the Institute, in Rome, at the Institute of Physics, which was located in Via Panisperna. And this group included Emilio Segrè, Enrico Fermi, Ettore Majorana, Bruno Pontecorvo. These photos, historical photos, was shown before. You can see Segrè, you can see Fermi, you can see Rasetti, you can see Amaldi. Edoardo Amaldi was also part of the group. You can't see Pontecorvo because he's the guy who took the picture. At the time, selfies did not exist. So otherwise, we will also have Pontecorvo in that picture. These people were known at the time for their pioneering work on slow neutrons. And what is most important, that they are considered to be the fathers of particle and nuclear physics in Italy. Particle physics and nuclear physics are very successful in Italy. Italy is a country that really is one of the leading countries in this field. And actually, our origin date back to that famous group of people who inspired generations of physicists like me. So the Higgs boson was discovered at CERN. What's CERN? CERN is the world's biggest laboratory for high-energy particle physics. And particle physics is the most fundamental of all sciences because it studies the smallest constituents of matter and of the universe, the so-called elementary particles, objects that cannot be cut into smaller pieces, objects that have no substructure. And particle physics also study the law of nature and of the universe at the most fundamental levels, at the short distances. And over the years, we learned that physics at the short distances is related to physics at the cosmic scale. So this photo is an aerial view of the Geneva region. The red line shows the border between France on the top of the screen and Switzerland on the bottom. You can see, if I have a laser pointer, you can see Lake Geneva, you can see Geneva Airport, and the white circle shows the position of the Large Hadron Collider, the most powerful accelerator ever built by humanity. It's a 27-kilometer ring straddling the border between France and Switzerland, 100-meter underground, where we inject in two beams of protons in the two opposite directions of the ring, and we accelerated them up to the highest possible energy, and we bring them into collision at 4 points of the rings where we have installed 4 big experiments, and I will get back to you, back to this later on. So, fundamental research is CERN's main mission, but CERN has a broader class of objectives which rest on 4 pillars: research, technology and innovation, collaboration across borders, and education and training. And I will try to illustrate all of them, starting from research. So what are the elementary particles that we study at CERN? I know that in the audience there are physicists for which this slide is boring. There are students for which the slides may be interesting, just to refresh their knowledge of physics, and also the general public. And so my slides are a little bit of collection of different levels of explanation and illustration, and I hope that they will be accessible or interesting to everyone. So what are the elementary particles we are studying at CERN? So we know that matter, ordinary matter, we are all made of, and the objects that surround us and the visible universe are made of atoms. Atoms are not elementary particles. They are made of a central nucleus surrounded by a cloud of electrons. Nuclei are not elementary particles. They are made of neutrons and protons, and neutrons and protons do have some substructures, which are called quarks. And as far as we know today, quarks and electrons are elementary particles, and therefore they are the fundamental constituents of matter. And the matter we are all made of, the objects in this room, the matter that makes up the visible universe. We are all made of electrons and quarks. The Large Hadron Collider allows us to study, to scrutinize matter at the level of the quarks. So on physical sizes of smaller than in billions of a meter. So this accelerator can be seen as giant microscope. If you want to study a human cell, a tabletop microscope in a lab, it's enough. But if you want to study structure like the quark that are 1 billion times smaller than human cells, then you need big accelerator because you need to inject a lot of energy into the system in order to resolve the smallest structures. So this study of this very, very small allows us to understand, gives us insight into the very, very large, so the structure and evolution of the universe. So we know today that the universe had origin some 13.8 billion years ago, from an initial state of very high energy density and temperature, followed by the very rapid expansion. And at the beginning, the universe was a gas of free elementary particles. So by studying the elementary particles and their interaction, we can understand how the primordial universe behaved. And with time, it expanded and cooled down, and the elementary particles combined to form structure of increasing complexity, atoms, molecules, light chemical elements, up to the macrostructure that we admire today, planets, stars, and galaxies. And there are several ways of studying the universe and its evolution. We can use telescope on Earth or in space. Telescope looks at the macro objects, and by studying the farther object, they can go back in time. However, there is a wall, some 380,000 years after the Big Bang, beyond which they cannot go, simply because before that epoch, the universe was so hot and dense that light could not escape, and so it never reached us and our telescope. Accelerators allow us to go to earlier times. And at the Large Hadron Collider, we are able to explore the universe at the time of millions of a second after the Big Bang, 10 to the minus 12 seconds after the Big Bang. What does this mean? It means that the energy that we produce in the collisions of the two proton beams that we accelerate and collide in the Large Hadron Collider corresponds to the temperature that the universe had at that time. And this temperature is 100,000 billion times the temperatures in this room. So we are able to reproduce in a lab the conditions that characterize the early universe. So clearly, to do this, we need powerful instruments. We need 3 types of instruments. We need accelerator to accelerate and collide particles. We need detectors to study the collision products. And we need a large computing infrastructure to store and analyze the large amount of data produced by those instruments. And of course, these instruments are extremely complex and advanced, and require the development of cutting-edge technologies in many fields at CERN and in the collaborating institutes. And these fields are typically superconducting magnets and materials, robotics, electronics, cryogenic, vacuum, big data, quantum, artificial intelligence, and so on and so forth. So I will say a few words about each one of these amazing instruments. So let's start by the collider itself. Again, you can see the ring, this time in yellow, underground. Operation started in 2010, and at that time we started exploration of a new energy frontier. So I said before that we inject 2 beams of protons in the 2 opposite directions, and we accelerate them up to the largest achievable energy, where the limit only comes from the available technology of magnets. Because what is difficult in a proton accelerator is not so much to accelerate the particles, but to keep these very high energy particles on a circular trajectory. It's like when you drive a car, the higher the speed of the car, the more difficult it is to keep the car on a circular racetrack. And so for this, we need very strong magnetic fields, and we need very powerful magnet. We'll see superconducting magnets. So the technology of superconducting magnets limit the energy that we can achieve in our accelerator, in our colliders. And we accelerate these 2 beams, and then we brought them in collision at 4 points of the ring, where we have installed 4 big instruments in 4 big underground caverns. These instruments are called particle detectors, and their task is to surround almost the full solid angle around the collision point and to detect the thousands of particles that are produced in each collision. Detect means detecting them, measuring the trajectories and of this particle, measuring their energies, identifying them. So if the accelerator can be seen as big, giant microscope, these detectors can be seen as giant three-dimensional cameras that take picture of the collision events for further interpretation in terms of physics. But the problem is that the two proton beams collide 40 million times a second. So these instruments have to be very, very fast. So it's a big challenge to take this 40 million picture. Of course, we cannot record all these pictures, otherwise we will not have enough computing resources. So the experiment have to select online the events that need to be, the collision that need to be recorded because they are interesting and they contain some interesting phenomena, and those that contain known physics that can be thrown away. There are 4 of them: ALICE, ATLAS, CMS, and LHCb. 2 of them, ATLAS and CMS, are called general purpose detectors because in principle they're able to detect any kind of, and study any kind of physics, known or unknown. ALICE and LHCb are specialized detectors that focus on 2 specific items. LHCb try to understand why the universe today is almost exclusively made of matter with almost 0 antimatter. So we will come back to this later on. And ALICE study the quark-Coulomb plasma, which is a state of matter that permeated the universe a few microseconds after the Big Bang. So the United States has made extremely, very significant contribution to all the components of this, to all the instruments that we need for this exploration: the accelerator, the 4 experiments, and the computing. And Berkeley teams have been significantly involved in the development of the accelerator, the ALICE and ATLAS experiment, and the software and computing. And here you can see an object that has been a component of the accelerator, which has been built here at Berkeley. Is a box, is a device that provides the electrical current to the superconducting magnets and also handle the interface between warm temperature and cold temperature, as we will see in a few seconds. So it's very high-tech object. This is a spectacular view of the underground ring, 27-kilometer ring. These blue tubes contain 1,232 high-tech superconducting magnets, which were developed for the first time for this purpose. And these magnets make the collider's backbone, and it's the single most important ingredient that allow us to make a jump in energy by a factor of 7 with respect to the previous collider, the glorious Tevatron collider, which operated at Fermilab, the DOE accelerator laboratory in Illinois, where the top quark was discovered. And then, of course, later on, the LHC took the leadership thanks to this, in particular to this magnet that allowed us to go to higher energy and the larger ring. So why superconducting magnets? Because we need to provide very strong magnetic fields, and so strong magnetic fields require high current. This magnet carry a current of 12,000 ampere, and only superconducting magnets allow us to produce and to transport currents, this level of currents, because they provide high current density and also current. They allow us to transport current with no losses because they have no resistivity. So only superconducting magnets can do this job. These magnets have been built in industry. However, prototypes were built at CERN, and I think it's important to underline the very special relation between fundamental research at CERN and in other laboratories in Europe and also here in the United States and industry. It's not just a client-supplier relation where we go and we ask for something, we give the money and we get it. Because many of these technologies do not exist in industry at the time where particle physics need them. And so particle physics is the driver of innovation because we need to develop usually prototype of this technology in-house, in our laboratory, together with industry. And then once the technology is mature, we transfer it to industry for the production of thousands of components and pieces. And so these magnets have been built by three leading industries in Europe, Alstom in France, Ansaldo in Italy, and Babcock in Germany, and are a brilliant example of partnership between CERN and industry. Detectors are also extremely challenging. This is a beautiful image of Atlas. You see the size of Atlas compared to 2 human beings. So the size of Atlas actually is half the Notre Dame Cathedral in Paris, but underground. So when you go to Paris, next time you go to Paris, you see Notre Dame, imagine Atlas is half of it underground. The other experiment is not less spectacular. The weight of the CMS experiment is 13,000 tons. So again, if you go to Paris and see the Tour Eiffel, the Eiffel Tower, its CMS weighs more than the Eiffel Tower. So you are, of course, fascinated by the size, but also the complexity is really amazing. These detectors have 100 million of sensitive elements. Most of them are concentrated in the innermost part. I will come back to this just in a few seconds. And the United States has contributed in a very important way to all sub-detector components of this giant instrument, and teams here in Berkeley, in particular, to the innermost and maybe I would say most challenging part of this detector, the silicon detector made of pixel and silicon strips, which is the most challenging because it's very close to the beam, a few centimeters from the beam line, and so it sees a high density of particles coming from the interaction, so it has to be radiation hard, it has to be very fast, it has to be very granular, provide excellent resolution, etc. And this is an image showing the insertion of the pixel detector, the most innermost part of Atlas, into the Atlas experiment before the LHC start operation in the years 2000 with the project leader Kevin Hansweiler from LBL. Computing, here also a great revolution. Before the advent of the Large Hadron Collider, typically the computing resources needed for a given facility were hosted by the laboratory where the facility was operated. So for experiment at CERN before the Large Hadron Collider, all the computing resources, disk, tape, processor were at CERN, and all the users from all over the world working on CERN experiment would access the resources at CERN. With the advent of the LHC, we realized that this was not possible. First of all, because the amount of resources required was huge, so it was not possible to have all of them at the same location, but also because, I will see in a few slides from here, the community of the LHC is really a worldwide community, and it will be totally impossible for all the people from all over the world to access resources at one given location. And so the community developed a new concept, which we call the Worldwide LHC Computing Grid. It's a distributed computing system. There are 170 data centers in more than 40 countries, connected by very fast and very efficient networks. And this grid provides the resources for the LHC, for the experiment, and for the physicist. We have 2,000 petabytes of storage space, so 2 exabytes of storage space, 1.4 million cores or processing cores, and so on and so forth. Being distributed also, it serves very well the worldwide community. It's organized in tiers. There is a tier 0, which is the main computer center at CERN, which is responsible for recording and storing the raw data coming from the experiment and for performing a first pass reconstruction of the data, then distributed to the tier 1, which are a medium-sized computing center. There are 2 of them in the United States, one at Fermilab, another one at Brookhaven National Lab, and then tier 2, which are smaller university type resources and computer center. There is one here at LBL. So to complete this part on the instruments, I've tried to collect in one slide some key figures that illustrate the technological challenges. So I mentioned before that the superconducting magnets work at low temperature. The LHC magnets work at 1.9 Kelvin, minus 271 degrees centigrade, centigrades, and so 1.9 degrees from the absolute zero. And actually, the full Large Hadron Collider, 2070 kilometer ring, is almost fully immersed in a bath of superfluid helium at 1.9 Kelvin, which makes it the most extraordinary, the biggest cryogenic system in the world. Protons travel very close to the speed of light, and so they make 11,000 turns of the 27-kilometer ring. These beams contain a lot of energy because they are very intense. In each beam, there are 200,000 billion of protons circulating in the ring, with carrying a very high energy. So the total energy stored in this beam is 400 megajoule, which is a very important, which is a very high amount of energy. And I was told, I don't know if it's true because I didn't measure it, that this corresponds to the energy of an Airbus running at 100 kilometers an hour on the tarmac. This was, I was told, so I hope it's true. Okay, so let's now move to the performance. These three instruments have been performing extremely well since the beginning of the LHC. Here you can see, as an example, the top plot shows the integrated luminosity delivered by the Large Hadron Collider to ATLAS and CMS. The integrated luminosity is a parameter proportional to the number of collisions that the accelerator delivers to the experiment. And so if you want to do, a lot of physics, study rare phenomena, you need a lot of collisions, and so the accelerator has to perform very well. We started in 2011, and we had until now 3 periods of data taking called run 1, run 2, and run 3. And you can see the progression in terms of energy. We went up in energy from 7.8 tera-electron volt to today 13.6 tera-electron volt. But also in terms of delivered amount of data, which has increased with time, and also the slope with which the accelerator, which was very steep in the recent years, showing an incredible performance. And actually for the experts in the room, the peak luminosity exceeds 2 times 10 to the 34 centimeters to the minus 2 and seconds to the minus 1, which is more than a factor of 2 the design value. So the accelerator was designed for 1 times 10 to the 34 and actually is operating on more than 2 times 10 to the 34. The bottom figure shows the schedule. So we are now at the end of the third run data taking period, run 3, which will finish mid-2026, and this will be the end of the first phase of the Large Hadron Collider. Then this will be followed by a long shutdown lasting for a few years, during which we will install upgraded components of the accelerators and of the ATLAS and CMS experiments, which will allow us to operate with higher intensity beams and so to produce more collisions. And this new phase, called high luminosity LHC, will start operation in 2030 and operate until 2041. So the high luminosity LHC will provide 10 times more collision than the LHC. And more collisions are important because we want to study rare phenomena, very heavy new particles produced in the collision. The Higgs boson itself is a rare process. And so the more data we have, the better, the larger is our sensitivity to rare phenomena. We want to measure the Higgs boson, and we'll come back to this later on, with increasing precision. And of course, the more data means more chances to discover new physics or new phenomena. The high luminosity LHC will use new technologies. In particular, you have now understood that superconducting magnets are important. The current superconducting magnets are based on a material called niobium titanium. And for the high luminosity LHC, we will make a step forward and use niobium tritium, which is a material also very much used for nuclear fusion, for energy production. And new superconducting magnets for the final focus of the beams are being built at CERN and in the United States at 3 national labs, LBL, Brookhaven, and Fermilab. And you see on the top a beautiful magnet produced in the United States with the 3 logos of Fermilab, Brookhaven, and LBL. And here you can see the magnet assembly line at LBL, very, very close to here. So let's now move to the physics. In July 2012, the ATLAS and CMS experiments announced the discovery of a new and very special particle, the Higgs boson. Why is it so special? Because it is related to the mechanism that allowed matter, the matter we are all made of, atoms, to form in the early universe. Without this mechanism, which is called Brout-Angler-Higgs mechanism, and which manifests itself through the Higgs boson, we will simply not be here. So you have to imagine that in the very early universe, all particles, including the electron and quarks, we have seen that electrons and quarks are the fundamental constituents of atoms, were traveling in the universe at the speed of light. And at some point, the Higgs field, which is a field that permeated the universe, activated itself, and these particles interacting with the Higgs field acquired a mass. And why this is important? Because if electrons and quarks were massless, atoms will not stick together, so we will simply not be here. So the Higgs boson is really linked to our life, and this is the first link of the Higgs boson with our life. So as I said, the Higgs boson is inextricably related to the very first moment of the universe, and may also be related to its fate. It's also related to some of the most important outstanding questions in fundamental physics. I will get back to this later on. And so, studying it in all details at the LHC and future more powerful colliders, it's very important to get insight on how the universe came about and how it will evolve. So how do we detect the Higgs boson in our instruments? How do we see the Higgs boson? The Higgs boson, once produced in the collisions of the proton beams, and this happens 1 billion, we produce 1 billion Higgs boson one Higgs boson every billion collisions at the LHC. The Higgs boson disintegrates itself immediately. So it decays in other known particles, electrons, photons, etc. And so by looking at the products, at the decayed products of the Higgs boson, we can infer the features of the mother particle, the Higgs boson itself, its mass and its features, characteristics. And here you can see a very nice peak in blue, showing a signal, the production of Higgs boson and decay around the mass of 125 GeV, which is the mass of the Higgs boson. This corresponds to 130 times the mass of the proton. So this is how we see the Higgs boson in our detectors. So since the discovery of the Higgs in 2012, the ATLAS and CMS experiments have made big progress in characterizing this very special particle. So, for instance, we have been able to make huge number of measurements of the production mechanism of the Higgs boson, illustrated on the bottom right part, and also measure the various decay into different final states. And you see the huge number of measurements that have been performed by CMS, but also by ATLAS, with precision that are typically at the level of a few percent. And the right top plot, this is more for the experts in the room, shows the linear correlation between the coupling of the Higgs boson to the elementary particles, thereby experimentally confirming the mass generation mechanism over 3 orders of magnitude. You see the fantastic, this fantastic line that shows how mass are generated through the couplings to the Higgs boson. CERN is not just a Large Hadron Collider. Actually, we have a compelling scientific program complementary to the LHC, which exploit the unique capabilities of our accelerator complex and offers opportunities to about 20 projects and a community of 3,500 scientists. The LHC experiments gather almost 10,000 scientists, but also this community is quite important. Because actually the Large Hadron Collider is only the last link of a chain. So you here see, I don't know if you see, this is the LHC ring, but you see that upstream of it there are smaller linear or circular accelerators called the injectors, whose primary task is to accelerate the proton beams step by step and also give them the right time structure before they are injected into the LHC for the final accelerator up to the top energy. But their secondary role, equally important, is to offer beams of different particles, different energy, different time structures that are used by a large number of facilities to carry out exploration and studies that are complementary to the collider. So we have for instance, a radioactive nuclei facility called ISOLDE to study nuclei and also to produce radioisotopes for medical application. We have the only dedicated facility in the world for the study of antimatter. We will get back to antimatter later on. We have experiments to measure and study rare decays. We have recently approved the construction of a high-intensity beam dump facility to study particles from the dark sector. So I would like to show you only one example of this program complementary to the Large Hadron Collider. And the example that I've chosen is the cloud experiment. Cloud is a very small and kind of niche experiment in the broad landscape of the CERN scientific program. However, it's important because it shows the breadth and the impact of what CERN does. The main goal of cloud is to study the impact of cosmic rays, from which we are continuously bombarded, on the formation of aerosol, which are nuclei for the formation of clouds. Aerosol, which gives rise to clouds, are currently poorly known and actually are the largest source of uncertainty in climate modeling, so in climate change modeling. I remind you that clouds have a huge cooling effect on the planet, and so being able to model the clouds formation is very important. So the cloud experiment is a large chamber containing a precisely selected mixture of gases which is able to reproduce the condition of the upper tropospheres. And then we send beams from our accelerator in this chamber to mimic the action of cosmic rays. And in 2024, Cloud discovered that isoprene, which is an hydrocarbon which is massively produced by tropical rainforest, drives aerosol particle formation. And this was a mystery, not understood why aerosol was so much present on tropical forests. And so it's a major biogenic source of clouds, which is enhanced by the impact of cosmic rays. And these results made the cover of Nature in December 2024. So I think this is a nice illustration of the variety of our program. Another important component of our program is the so-called CERN neutrino platform, which was established to support the participation of Europe in an important flagship experiment and facility here in the US. The experiment is called DUNE, and the facility is called LBNF, Long Baseline Neutrino Facility. This experiment, this project, consists of sending beams of neutrinos from Fermilab, an accelerator lab in Illinois, to a detector located in an underground lab in South Dakota, 800 miles away. Neutrinos are very mysterious and intriguing particles. We don't understand their behavior fully. And while traveling from Illinois to South Dakota, neutrinos oscillate. That is, they change from one species to another one, a quantum mechanical phenomenon which we don't know fully. And so the receiving detector will study neutrinos when they arrive in South Dakota and try to understand how they behave. Their behavior also can be probably also related to the matter-antimatter asymmetry in the universe. So at CERN, we have been developing and testing a series of prototypes for the DUNE detector. These are very, very big, large liquid argon tank. You see here one here in red, containing the cryostat contain 17 kilotons of liquid argon. So CERN has been developing, with a collaborating institute, been developing and testing a series of prototypes, which were a process which was crucial to validate the technology. But we are also constructing these two big cryostats for two modules of the DUNE experiment. And you see on the top right, on the bottom right figure, components of the external wall, or the warm wall of the cryostat being transported to the US. So these detectors, as I said before, require the development of frontier technologies. These technologies are transferred by CERN to society at no cost. CERN indeed embraces and promotes open science, meaning open access publication, open source, open hardware. This is enshrined in the CERN Founding Convention, which is a document signed in 1954. I will come back to this later on, which states that everything we do at CERN, every physics results, every development must be made available to society free of charge. So the most famous example is the World Wide Web, which we use every day, which was developed at CERN in 1989 by Tim Berners-Lee, who was a CERN employee. And then in 1993 was made available for everyone to use and develop at no cost. Other examples of impact of CERN on society include accelerator to treat cancer using protons and light ions like carbon ions, which is a therapy complementary and in some cases for some types of tumor more effective than X-rays, which has the advantage that protons and light ions can be focused on the tumor target. So they just hit the tumor, they release all their energy there and they destroy the tumor. On the other hand, X-ray tends to spread also in the surrounding healthy tissue. Another example are electronics for medical imaging. You can see here a rather disgusting, I must say, three-dimensional scanner of a wrist, but you can see the precision, colorful, three-dimensional taken with CERN electronics. Our electronics and AI development is used today for autonomous car driving. We have a collaboration with Volvo. You can see in the bottom central part of the screen a dosimeter, so an instrument to measure radiation on board of the International Space Station. And here on the left bottom part, left corner, you can see superconducting cables which can carry a lot of current. These cables have a cross-section of a few centimeters and they can carry 120,000 ampere with no losses. Of course, these are used for a high luminosity LHC, but we have a collaboration of Airbus which wants to develop clean airplanes. Of course, you know, these cables are very light. If you had to carry the same current, if this is possible, with normal conductor, you will need very, very big and massive cables, and with superconductors, you get just these very light cables with no losses. Okay, so what's next? There are many outstanding questions in fundamental physics, in particle physics in particular today. So first of all, we have been very successful because today we have a theory, a very successful and phenomenal theory called the Standard Model. And all the particles predicted by the Standard Model, you can see them there, and I will make a few comments later on, have been discovered experimentally. And all their interaction, how they behave, have been measured with extremely high precision at accelerator from all over the world, and they are in perfect agreement with the Standard Model expectation. So the elementary particles, the spectrum of elementary particles that we know today are shown there. There are three different classes of particles, quarks and leptons. These are called matter particles because the first generation, the up quark, the down quark, and the electron are the fundamental constituent of matter. You remember that I told you that atoms are made of quarks and electrons, in particular of up quark, down quarks, and then electrons. So those three particles are three notes on which we build the music and the symphony of the visible universe. Then we have particles that are force carriers, in purple there, that are responsible at the microscopic quantum level of the transferring force. So for instance, the electromagnetic interaction between two electrons happen through the transfer of a photon. And similarly, the Z and W particles are responsible for carrying the weak force, which is responsible for radioactive decays or thermonuclear reactions in the sun. And then you see the Higgs boson, which is by itself, because as I said, it's very special particles related to the mass generations. So these things are very well understood, and with the discovery of the Higgs boson, we have completed the spectrum of particles. So we should be happy, but actually we are not so happy because there are many open questions to which the Standard Model, so we human beings, are not able to answer today. So we don't understand why, for instance, there are three families of quarks and leptons, whereas only the first one is actually used to build up matter. We don't understand why the Higgs boson is so light. We don't understand why the universe today is almost exclusively made of matter. Antimatter is as nice and pleasant as matter, despite some movies, okay? And we think that at the beginning of the universe, at the time of the Big Bang, matter and antimatter were present in similar proportion in the universe. And then something happened, we don't know what, and matter disappeared. We don't know where it went. And today we live in a universe that is made almost exclusively of matter. We are happy with this because matter and antimatter have the bad habit that when they get together, when they interact, they annihilate and disappear. So if matter and antimatter had persisted in equal proportion, we will not be here. However, we would like to understand, okay? And this we don't know today. I mentioned that neutrinos are extremely mysterious, still extremely mysterious particles. And then, of course, there is all the problem of the dark universe. You know that when you look at the sky, you see the beautiful star, galaxies, and planets, and you add up all this visible part together, this only accounts for 5% of the universe. The rest, 95%, is a question mark. It's made of form of matters and energy that we do not know and which do not interact with our instruments, and for this reason, for these two reasons, we call them dark matter and dark energy. Dark matter is responsible for holding galaxies together. Dark energy is responsible for the current accelerated expansion of the universe, and actually this is something which was discovered at the end of last century by looking at distant supernovae by two teams, one of which led by Sol Perlmutter from here, from LBL, who also received the Nobel Prize for this discovery. So the questions are so important, so different, although they are interrelated, they are so different and so complex that there is no single instrument that can answer them all. And the best thing we can do as scientists, as human beings, is to deploy the various approaches that we have developed over the decades, thanks also to the fast development of technologies that include accelerator, colliders, cosmic surveys, underground experiments, etc., in order to be able to address those questions. In dark blue, you can see in particular the questions that are directly accessible to a future collider, in particular using the Higgs boson as a discovery tool. The Higgs boson, like neutrinos, like gravitational waves, is a very powerful discovery tool because there are many things about this particle that we do not understand. It's related to some of the questions in the top box, but also, and this is more for the expert in the room, it's related to the most obscure sector of the Standard Model. If you look at the Standard Model equation, the so-called Lagrangian, you see that all the terms that are puzzling, which we don't know answer and we cannot describe, like the flavor, the naturalness, and the vacuum stability, they all involve the Higgs boson. So there is something peculiar and in this particle that we must understand. So what is the next collider at CERN, which will try to address some of these questions? So today, the preferred direction is the so-called Future Circular Collider. So you can see a sketch on the top right part of the screen. You see the LHC, 27 kilometers, which looks ridiculously small compared to the FCC, which is a 90-kilometer ring. So it will be a 90-kilometer ring. But it's not just bigger. There is also, it will also contain a much more advanced accelerator, so new technology. There will be 4 collision points, so 4 experiments, as today at the LHC, and it has an immense physics potential. It will be, if of course implemented, if realized, it will be an extraordinary instrument to study the fundamental laws of nature at the shortest distance and their link also with the cosmic scale, and to nail down the characteristics of the Higgs boson and understanding its role in the birth and evolution and fate of the universe. As I said, we will need to push the technologies beyond the current knowledge. The time scale, the project may be approved around 2028, and a few years from now, construction may start in 2033. The first stage operation will be an electron anti-electron collider, a so-called Higgs factory, which will produce millions of Higgs bosons in a very clean environment, so it will allow us to study the Higgs boson in all details. The second stage will be a proton-proton collider, like the Large Hadron Collider today, but with almost 10 times more energy. And I want to show you this nice photo because in June 2024, the FCC community had their annual meeting in San Francisco. It was a very successful event attended by almost 500 participants and co-organized by LBL. the FCC is not the only option for a future collider at CERN. There are also linear colliders that accelerate and collide electrons and positrons coming from the two ends of the line. And there are also ideas as a next step before going to the next big machine to reuse the current LHC tunnel, a 27-kilometer ring for electron-positron collision or electron-proton collision. So the European particle physics community is currently in the process of upgrading its roadmap, also with the participation of US scientists. And one of the goals of this upgrade, which will be concluded in a few months from now, is to select the preferred option for the next collider at CERN and a prioritized list of alternatives. So all this will be impossible without our founders. A group of visionary scientists and politicians, among which US physicist Isidore Rabi, who in the early 50s understood that it was of crucial importance to create a lab, a big lab, that could carry out excellent scientific research in Europe. Also, first of all, to reestablish scientific excellence after World War II, but also to counteract the brain drain, Fermi, Segrè, etc. The second goal was to foster peaceful collaboration among the people and the countries of Europe after the war through science. So these founders really had a very modern vision. They understood that the socio-economic recovery of Europe after the war also requires sustained investment in fundamental research, number one. And number two, science is a glue that can connect people in a fractured continent. 12 member states signed the founding convention in 1954. Today, CERN has 25 member states, 9 associate member states from all over the world, from Brazil to India to Pakistan and Ukraine, and 4 observers, among which the United States. We have an annual budget of 1.2 billion Swiss francs. It's $1.5 billion, which is equivalent to a medium-sized European university. And we have a population of 17,500 people, representing more than 110 nationalities, working at CERN and coming from more than 600 universities and institutions from all over the world. So CERN is really a global laboratory. Many of these scientists come from the member states, but actually the largest contingent come from the United States, with more than 2,000 scientists involved in CERN programs. Some of our scientists come from countries that do not entertain romantic relations with each other, and some come from underserved and low-income countries that do not invest much in science and technology. You see some of them here, from Algeria to Morocco, Madagascar, etc. And so in this case, our mission is capacity building. So if you look at the age distribution of this population, you see that the peak is at 27 years. So our population is mainly made of young people, student and postdoc. I am also in the 27-year peak, and I will not move from that peak. So training is one of our primary missions. And at any given time, CERN is training some 5,500 young people, including physicists, engineers, and technicians over a large number of fields. Now, typically, only 30% of these young people remains in particle physics. The other find jobs in other fields, mainly in industry or other public institutions. So CERN and the collaborating institution provide society with a continuous flux of young talent trained in STEM, science, technology, engineering, and mathematics, a workforce that society desperately needs. And it's also very important to share with society the importance, the beauty, and the utility of science. And this was one of the main goals of the CERN Science Gateway, along with inspiring the young people to undertake scientific studies, because in no way we can hope to address today's global challenges, from health to climate change to the environment, without the support and the help of science and technology. So the CERN Science Gateway is our new flagship center for communication and outreach, targeting the general public of all ages. You see it's made of 2 tubes and 3 pavilions. It's really beautiful, 7,000 square meter. It includes immersive exhibition, education, pedagogical labs for the very small kids, scientific shows and various events. We opened it to the public exactly 2 years ago, and we have welcomed since then almost 800,000 visitors from 179 countries. We also host high-level events. We had an evening with former Vice President of the United States, Al Gore, to discuss global challenges and the role of science, and an evening with famous cellist Yo-Yo Ma. So a few words before concluding on the partnership between the United States and CERN. It's a long-standing and extremely fruitful partnership. Actually, the United States is our closest partner of all the non-member states, and as I mentioned, the US has the largest collaborating community among all CERN users. Before the advent of the LHC, the United States has been involved in many experiments and facilities at CERN, and in 1994, the US, after the shutdown and the introduction of the SSC, officially joined the LHC research program. And here I would like to honor 2 people that have been absolutely instrumental in this endeavor, in the US joining CERN. One is the late George Schilling, and the other one is Martha Krebs, both from LBL. And in 2015, CERN joined the LBNF Dune project. And last year, at the White House, we signed a statement of intent between CERN and the United States to collaborate on future large research infrastructure, advanced computing, and open science. And this document also includes collaboration of the United States on the future circular collider. DOE, NSF, and the national labs, universities are very strongly involved in the LHC experimental program, in all 4 experiments, but also beyond that, also in other experiments as part of our broader scientific program. I want to show you 2 pictures. One shows the clean room here at LBL for the construction of the silicon strip modules for the upgrade of the Atlas inner detector for the high luminosity LHC, a high-tech detector. And the other one, these are staves of silicon sensors built at LBL for the ALICE detector inner part that are being transported to CERN by an airplane. You can see they have their own seat, they're watching a movie, so what they're doing. But anyway, again, very strong competencies here on high-tech silicon detector. And I would like to conclude with this beautiful image of the sky taken by the James Webb Space Telescope. When you see images like this one, we are of course all fascinated by the luminous object, stars and galaxies. However, for us particle physicists, like for astrophysicists, cosmologists, astronomers, the most intriguing part is the dark part and the vacuum. It's true, my eye actually in this picture sees the dark part, because the luminous part, we know it, we understand it. What we don't understand is the dark part. I mentioned the dark universe, 95% of the universe is a question mark, so this is an important frontier of physics. But also the vacuum is not empty in physics. Suppose that we all go out of this room, we take all the furnitures and objects out of the room, we bring in big pumps, we absorb up to the last molecule of air. This room is not empty. There is a Higgs field, there is energy, there are particles flashing in and out, but we don't understand the energy of the vacuum, we don't understand its structure, its energy may be related to dark energy and to the expansion of the universe. So the dark universe, the vacuum, neutrinos, and the Higgs boson, in my opinion, are the next frontiers in fundamental science. Thank you.
So thank you to Dr. Gianotti for a beautiful talk. We will take a few questions. So let's see, hands up. I will start with one.
Oh, good.
You laid out a few of the open questions in science, in particle physics. If you could wave a magic wand and answer one of them, which would it be?
Dark universe.
Okay.
It's a little thing. It's just 95%. Even dark matter, 25%, will allow to increase our knowledge of the universe from 5% to 30%, which is, of course, very good. But the dark universe is something really intriguing.
I see a question here. I think we have microphones. Microphones will be brought. If people could make space in the aisles so the microphones can get to the questions.
Hi, thank you for the talk. As a earlier career research, like in science and generally, all these projects that you talk about are potentially can consume like an entire career, for example. How do you think about motivating, say, these large-scale research projects amongst the newer generation, and generally thoughts about that, either structure-wise or science in general, other than the exciting science being motivated
So the question
here?
is how to motivate the young generation to, to undertake these big projects. Yeah, it's a very good question. These are, of course, projects that take many years, of course, to conceive, design, build, and then operate. But this is true for, in general, for big science. Telescopes are bigger and bigger, accelerators are bigger and bigger, and projects are longer and longer. We are the victims of our success. Now the easy, low-hanging fruits have been discovered. Now we have to go deeper, go farther away. And so this is part of fundamental research today. I think the motivation, and I can tell my motivation because I've also been a young student in just a few years ago in one of these. Don't laugh, it's not nice. No, sorry, just a few years ago, and so. These big projects are long lead projects. However, they are interesting because you go through many phases. You can participate, you can be involved in the R&D to develop the detector technologies, which usually are very challenging because, of course, as we've seen, these instruments are very ambitious. Then you operate them, then you do the physics of them. So it's an ensemble of things. It's addressing very intriguing and sexy question with advanced technology, doing it in a truly international group with people from all over the world. I think all these facets together are important components of what we do. Also, this instrument, like for instance the collider, are environment where you learn a lot of physics. You may be working on a specific analysis, on a specific detector, but then when you go to the collaboration meeting, you are exposed to a huge amount of different physics activities, different detector technology. So it's a very enriching experience.
Thank you. Other questions? There's one down here at the front. Microphone's just coming.
I can't see anyone. Yes.
Thank you, Doctor, for the talk. And I'm very impressed at the scale and the advancement humanities was able to make. And for such a massive machine or instrument, what are some maintenance that you need to do and how often you need to do them to maintain such an instrument?
Didn't see. What did I say? Maintenance of experiments. Yes. Yeah. Well, maintenance of these big objects, of course, is very complex. First of all, they are equipped with many thousands of sensors. For instance, the detector and the accelerator itself sensor, which allow us to track any deviation, any movement, and see how they behave. But we actually invest a lot in maintenance and upgrade of the experiments, of the facilities. You see that we have a budget of about 1.3 billion Swiss francs, and actually most of this budget, 800 million or so, is invested in maintaining, operating, upgrading these facilities. So it's very important to. But I must say that, first of all the three components of all the three instruments of our field, accelerator, detector, and computing for the LHC project, they perform well beyond the most optimistic expectation. We have seen the accelerator operates at much higher luminosity and intensity than foreseen. The detectors are extraordinary in terms of performance, and we are dealing with challenges like the overlap of the various colliding bunches well beyond what was predicted at the beginning. The computing also is amazing what the computing manages to do with a huge amount of data. So this means that this detector, computing, and accelerator were built with very, very well, that the field, the community is very strong because it's able to deliver and to, and we are able to perform better than foreseen, but also that we are able to maintain them and to, after all, these are relatively old instruments. The detectors were built in the mid-90s, so they are 30 years old and still they work extremely well, and likewise the accelerator.
There's a question right here. Yep. Microphone's coming from here.
Hi, thank you so much for the talk. It was
you.
really cool to see. I'm wondering, the timescale of these projects you measure in decades, and I'm wondering how quickly is a project like this able to adapt to, say, a new advance in superconducting magnets? Are you guys able to incorporate new advances relatively quickly, or?
It's a very good question. Yes and no. Of course, you can't change things every 10 years. Now we are upgrading the Large Hadron Collider. We are using more powerful magnets for the final focus to increase the luminosity, but most of the accelerators remain the same. We are now upgrading the detectors, the ATLAS and CMS, in a very substantial way, but until now, the past 30 years, they've been pretty the same. So we can keep up with the technology, hardware technology at the level of every 10, 15 years or 20 years or so. But nevertheless, as I mentioned before, this detector performs very well also with the so-called old technology. What, of course, in evolution, of course, comes from the software. AI, machine learning. These technologies, the software technologies, this can be followed up and can be deployed and used, and we can follow up with the technology and we can use it as it is developed. It's more the software part. Typically, the upgrading technologies every 15, 20 years.
Cool. Thank you so much.
There was another question right behind you.
Thank you so much for the presentation. I was wondering, as you mentioned, the larger collider is going to be built, hopefully. Is there something that theorists, scientists are hoping or expecting to find when colliding particles at higher energies?
Yes, we hope to be able to answer some of the questions that I mentioned. For instance, if dark matter is made of heavy particles, they could be produced at the FCC proton-proton collider. I can't tell you what. I mean, today, we are, there are open questions. We are trying to address them and to give an answer to those questions. I can't tell you which one we will be able to answer, but for sure we will make progress in our understanding of the laws of nature. Of course, when you discover a new particles, you get the headlines of the newspapers. Everybody's happy and excited. But equally important is to measure the particles that we know, measure the phenomena that we know with increasing precision, because this gives also some hints of possible new physics. And at the end, what we want to do is to improve our understanding of how nature works at the smallest distances. So I can't tell you what we will discover, if we will discover a new particle, a new phenomenon or not, but for sure I can tell you that we will make great progress for humanity.
Thank you. Let's have one more question over here.
Thank you so much for the talk. I was wondering if CERN had any outreach programs or any opportunities for undergrads and grad students to get involved in research.
Undergraduate program, absolutely, yes. We have internship, we have a summer student program, which brings to CERN every summer 300 students, 150 from the member states, 150 from non-member states, so US nationals are eligible. And these young people spend 3 months at CERN. In the morning, they follow lectures, high-level lectures, also given by Nobel laureates. And in the afternoon, they are integrated in the experimental teams, in the accelerator, in the experiments, in the computing center, and they work with the teams at CERN. This is an example of a nice program. There are also many internships. So there are many, many opportunities. If you go to the CERN webpage, you will find them.
Let's do just one last question. I'm seeing one right here, sort of halfway back on the right. Yep. Perfect.
Oh, thank you once again for the talk. I was wondering more on how the repeated mention of the dark universe and the dark matter, how the future colliders could affect possible research on dark matter and influence potential models and theories you have for dark matter, and how the new information could affect it.
So dark matter, we don't know very little about dark matter. We don't know if can be made of extremely light particle or extremely heavy particle. So it's a full mass range over several orders of magnitude. So if dark matter happens to be in the energy range of a few hundred GeV to a few TeV, colliders are among the best tools to produce it and to study it. If it is extremely light, then we have no chance. Okay, so it depends on where nature is. And concerning dark energy, of course, discovering new forces, measuring the Higgs boson, understanding, the contribution to the energy of the vacuum can be something useful also for the dark universe, for the dark energy part.
Thank you.
So thank you. Let's thank you.